Waste heat is often a byproduct of many processes, and usually it's just dissipated into the environment. There are ways to recover it, and one of these ways is by using thermoelectric materials. Thermoelectric materials can convert energy between heat and electrical forms. These materials are governed by the Seebeck effect, where for a temperature gradient there is an opposing electric field. These materials are also quantitatively described by the thermoelectric figure of merit ZT. It describes how good the thermoelectric system performs. To get a high ZT, one would want a high Seebeck coefficient and high electrical conductivity, as well as low thermal conductivity. J. Mulder in 2006 derived equations for thermoelectric properties using the free electron gas model. These equations are shown in the slide. In calculating for temperature dependence, it is important to remember that varying temperature also varies the chemical potential. This is how the temperature dependence was investigated. The figure in this slide shows the algorithm used for finding temperature dependence. These calculations were carried out in Python using values for the material bismuth telluride, a material commonly used for room temperature thermoelectric applications. Natural units were also used. The plot on the left shows the calculated chemical potential, and the plot on the right shows how it compares to the chemical potential from the Sommerfeld expansion. We see here that the calculated chemical potential follows the same trend as the one from the Sommerfeld expansion. These two plots show the thermal conductivity and the Seebeck coefficient's temperature dependence. Electrical conductivity was not shown as it remained relatively constant from low to high temperature ranges. Thermal conductivity decreased at a very high rate as the temperature increased, while the Seebeck coefficient displayed a peak at about 200 to 250 Kelvin, and then started to decrease rapidly at higher temperatures. Finally, this plot shows the figure of merit for bismuth telluride, where we see that it peaks where room temperature applications would fall into. In conclusion, the equations used here may be used to predict the temperature dependence of materials that fit the criteria for a free electron gas.
Today, I will be discussing our work, Excitation of a conserved lattice gas model as a possible toy model for granular systems. So a brief intro on granular materials. They're easy to define by example and are very common in industry. Despite that, their dynamics are highly unclear. There have been many experiments, though such experiments can be quite costly, and many methods have been developed to simulate such systems. In our work, we want to take advantage of the simplicity of the conserved lattice gas model in order to create a toy model for granular systems. We set up the CLG model as a 1D cellular automata lattice, where each cell can either be occupied or empty. Particle states are then determined by the occupancy of its neighbors. Particles can either be blocked, active, or isolated. If the particles are active, then they can move according to this rule set. In our work, we added the coefficients m and c, which represent mobility and cohesiveness respectively. This allowed the particle to be more active and represent shaking in the system. A higher m corresponds to a more free-flowing system, whereas a higher c can correspond to jamming. So in our results, we look at two main parameters, delta, the amount of change among the particles, and the active time. What we found in our work is that adding more activity caused the system to reach a steady state sooner as compared to the previous work. And we found that the delta values follow a Gaussian distribution, which further reinforce the steady state being achieved at an earlier time. In conclusion, we were able to better simulate a realistic granular system, which can be further used in investigating granular systems. For any questions, please email.
Good day, everyone. I am Jersey Dayan Yending, and today I'm going to talk about cluster behavior in a finite 2D Ising model with central block regions. For this study, we have a 30 by 30 square lattice with finite or non-periodic boundary condition and regions without spin at the center. Using this system, we try to ask, how will clusters behave in a 2D Ising model with regions without spin? To answer this, we varied the temperature and the size of the block region N and simulated 2D Ising model itself using the Monte Carlo Metropolis algorithm, as what we did for these example simulations. From the simulations, we found that as the temperature increases while n is held constant, the number of clusters also generally increases. Such behavior is more prominent for those with n less than 28. Having more clusters at higher temperatures imply that cluster size becomes smaller. And from our findings of the largest cluster size ratio per temperature, we indeed find that the cluster size becomes smaller for increasing temperature. So we further expanded the previous results to its corresponding spin-up and spin-down domains. For the number of clusters, there seemed to be no general trend for n less than 28. However, for the number of spins for n less than 28, there's a decreasing difference between the spin-up and spin-down count as the temperature increases. For both plots, the number of clusters and the number of spins equals for all temperature points for n equals 28. From previous studies of a similar system, this is due to the change in dimensionality of the system for the extreme case. That's all. Thank you.
Good day. I am Tim Rodriguez, and with my co-author Christine Villagonzalo, I will be presenting our paper on 2D electron motion with applied electric fields in the Drude model. So first, we'll look on the Drude model and its significance, and the implementation of the Drude equation on electron motion with 4 different applied electric fields. Finally, the results obtained from the program, including the physical properties derived from the plots, will be presented. In the study of emerging materials, the response to modulated fields provide a good picture of their properties. The Drude model provides a description on electronic behavior, especially in metals. Hence, in this research, it is used to see which properties can be seen with the given systems. So this is the Drude differential equation. 4 cases are applied and implemented in Fortran using the Runge-Kutta-Core method. And now here we see the momentum versus time curve with the zero applied field curve. We can see that the momentum decays consistently with the solution to the differential equation. It is also important to note that the momentum saturates to a non-zero value. This agrees with quantum mechanics. For the sinusoidal E field along X and the remaining others, however, initial momentum is set to 0. There is a spike in momentum, then an almost exponential decrease after the max speed. Gentler momentum decay slope is also seen because of a continuous applied field. Exponentially decaying field plot is almost similar to the E field pulse along Y, except that for this case, the decay curve is sharper because the field is immediately turned off. Also, the current was calculated at the maximum and is at the magnitude of 10 to the minus 12. So in conclusion, plots provide a general picture of electronic behavior when subjected to different environments. Qualitative properties are consistent with known physics, and physical properties like the current density can be calculated. So here are my references. Thank you.
Good day, everyone. I am Krishna, and my fellow author is Dr. Christine Villagonzalo. This is the characterization of phonon density of states of a graphene junction beyond nearest neighbor interactions. The aim of this paper is to create a systematic method in acquiring interactions in a graphene junction and to characterize phonon density of states by adding next nearest neighbor interaction and varying the bond stretching force constant of these said interactions. The thermal transport system used in this paper consists of the heat source, graphene junction, and a heat sink. This configuration induces a temperature gradient causing heat to flow from left to right. Also, in this system, carbon atoms are connected by springs, each with a bond stretching force constant we call Kf. First thing we do is to acquire the Hamiltonian matrix where we calculate potentials per interaction. To do this systematically, we slice the graphene junction of 48 carbon atoms into 3 horizontal layers and 4 vertical layers. We then have dimensions 96 by 96 for the Hamiltonian matrix, where it's divided into 2 types, intralayer and interlayer. We divided the Hamiltonian matrix into several matrices to carefully account all interactions. These 8 by 8 matrices pertain to interactions within a single unit cell and its interactions to its neighboring cells. After getting the total Hamiltonian matrix, we calculated the eigenvalues using Fortran 95 and plotted the phonon density of states. We noticed that adding next nearest neighbor interactions widens the distribution of energies. And when we vary the bond stretching force constant from 0.23 to 1.38, it also showed that strengthening next nearest neighbor interactions also widened distribution of allowed energies, and there were lesser available energy states per energy bin. These findings are useful in observing thermal transport properties of graphene, such as phonon transmission. From these results, we expect a weaker phonon transmission per available energy state when adding next nearest neighbor interaction. Thank you.
Good day. My name is Jose Mahalintal, and together with Dr. John Rob Bantang as co-author, I'll be presenting the dynamics of an interacting Bak-Sneppen system. The Bak-Sneppen, BS for short, is a simple model of biological evolution wherein n amount of species are connected in a ring, and each species is given a random measure of survivability known as a fitness value. The evolution of this system is determined by two rules modeled after concepts of real-world evolution. The first rule is that the lowest fitness is replaced with a new fitness similar to the idea of natural selection, whereas the next rule is that the nearest neighbors of F low are also replaced to incorporate the idea that fitness is relative. In our work, we explore the idea of interacting Bak-Sneppen systems by creating a 2BS system, one with symmetric interactions and the other with biased interactions, which we have termed as virus-host system. There are many ways to measure the spatial and temporal dynamics of the Bak-Sneppen system. What we have found was that the interaction models behave with similar dynamics when compared with the original model across all these spatial temporal properties. While no other literature is known that studies the effects of simultaneous BS rules, explanations towards the similarity between our model and the original can be pointed towards studies on the BS model on random graphs. Further findings and literature also suggest that BS dynamics is robust to many modifications, except in dimensionality and nearest neighbor interactions. If changes towards the BS dynamics is to be seen in the future, studies are to be dedicated towards this field. Thank you.
Hello, Chester here. It's too easy to take turn signals for granted. Yellow signal makes people step on the gas pedal and they're all eagerly waiting for that red countdown timer to finish. But at its core, traffic signals can be viewed as control systems that optimize vehicle flow. Optimized traffic means reduced travel times, which everyone definitely likes. Well, what else counts as a control system? Sometimes the traffic enforcer will intervene by turning off these stoplights. They look at the road, get a feel of when a road is too filled up, and wave their hands to drain the vehicle queue. Looks dumb, but it definitely counts as a local traffic signal control scheme. Let's consider three schemes. A null algorithm where the timings are predefined, a max queue scheme where the sensor looks at how many vehicles are queued up, prioritizing which has the most cars, and a max pressure scheme which, just like the max queue, but also you consider how many cars are present on the incoming roads. We analyze how the deployment of these will affect the travel time. Let's start with the trivial stuff. Obviously, if you encounter many intersections with turn signals, your travel time would significantly increase. If you get to be the unlucky driver that encounters 10 times more turn signals on your way to work, your travel time would be longer than what you feel like it should be. Being a bit smart about turn signals and adding a feedback mechanism would definitely improve travel times, even much so for those unlucky drivers. Now it's tempting to say, get rid of all those stoplights and replace them with hands and eyes. The details of these distributions are interesting and definitely non-trivial. Instead of looking at just the mean travel time, let's also take a look at how it is for vehicles that are part of the 95th percentile, the unlucky ones. Well, the max pressure algorithm keeps the travel time of the average driver optimized as the number of turn signals encountered increases. A lot of these tail-end vehicles get 2 or 3 times longer travel time. And here comes the trade-off part. In the MQ and MP schemes, vehicles that pass through roads that do not feel quick are part of the 5% tail. As tempting as it is to make all traffic systems intelligent, policymakers would have a trolley problem-like decision. Smart turn signals will make travel times for a lot of people better, but that's at the cost of some drivers taking really long rides. They will ask, do these tailed-end drivers deserve this, and how much would feel fair? Take a look at our paper in the conference program. Chester here, thanks.